Before we start to program, let's look at the structure of a typical application. One, get device list. 2, open the requested device. 3, query device capabilities. 4, allocate a protection domain to contain your resources. 5, register a memory region. 6, create a completion queue. 7, create a queue pair. 8, bring queue pair to ready to send state. 9, create address vector or vectors. 10, post work requests. 11, poll for completion. And 12, cleanup. Steps 1 through 7 are for creating the resources, context operations. Once a device has been opened, we can get specific information about a device and its ports, create completion queues and protection domains, which can be used for further operations. In Step 8 and 9, we configure the queue pair and the remote peer address vector. Finally, in Step 10 and 11, we perform the data send operation, and Step 12 shows us how resources are destroyed. Welcome to the RDMA programming training as part of the Mellanox Online Academy. This tutorial will explain how to find your RDMA-capable devices from a command shell. Let's start. First, you will need to connect 2 devices back-to-back or through a switch. Install latest Mellanox OFED. To proceed, click the question mark icon to learn more about Mellanox OFED. You need to identify the RDMA-capable devices in your system by running the command ibstat. Let's review the output. You need to be aware of the medium you are planning to use for your RDMA connection, InfiniBand or Ethernet. Mellanox RDMA-capable adapter cards may be equipped with 1 or 2 ports that might be configured to run InfiniBand or Ethernet. In this tutorial, we will use 2 Mellanox adapters with 2 ports. If your adapter is capable of running both InfiniBand and Ethernet, learn here how to change the adapter port type to your desired protocol. Next, make sure that the ports are enabled and up. If you run InfiniBand, make sure that OpenSM is running on the system. You can make sure that connectivity between the ports works by using ping. Our goal is to show a programmatic way to retrieve a list of devices present in your system. We start by creating a makefile to build our operation. Note the use of the libib verbs library is to allow access to the network adapter for RDMA-related operations. The library handles the control path for creating, modifying, querying, and destroying resources. It handles sending and receiving data from queue pairs and receiving completion queues. Download the complete ready-to-use makefile from the RDMA programming course page. In the following tutorial, we will learn how to enumerate the devices, understand which devices are present in the system, and find the type of the devices. Our goal is to retrieve and display the list RDMA capable devices. Open the file devicelist.c. In this file, we use IBV getDeviceList, returning an array of RDMA devices. To proceed, click the question mark icon to learn more about IBV getDeviceList. It is the user responsibility to call IBV free device list to free the memory allocated in the IBV getDeviceList array. Our first goal is to print the name of the devices by calling IBV getDeviceList. This will allow us to enumerate the adapters and get their symbolic name. Compile the example by running make in the source directory. We are now ready to execute the example by typing IBV getDeviceList. The result is the RDMA capable devices. For further information and to examine your knowledge, download the complete ready-to-use C file from the RDMA programming course page. In this tutorial, we will learn how to query capabilities and attributes of RDMA devices. Open the file devinfo.c. Let's take a closer look at the different file parts. Our aim is to scan the devices and to show their capabilities. We will print the capabilities of the device and its ports by using print HCA cap. Let's explore what print HCA cap does. First, we will open our devices by calling IBV open device. This function opens a device and creates a context for further use. To proceed, click the question mark icon to learn about IBV open device. Capabilities of a device are queried through IBV query device. The structure device attr contains the returned attributes. To proceed, click the question mark icon to learn more about IBV query device. Let's take a closer look at some device attributes. Max QP, maximum queue pairs, the total number of queue pairs the device supports. Max QPWR, maximum number of work requests. Max SGE, maximum scatter and gather requests. Also max CQ, maximum number of completion queues. Max CQE, maximum size of each completion queue. Max MR, maximum number of memory registrations. Max MR size. Maximum memory size is the largest memory registration that the device can create. Max PD. Maximum number of protection domains. Now it's time to compile. Type make. Type ./IBV-devinfo-d MLX4_0-v less to retrieve the device that we want to access. Let's review the example output. The adapter card is MLX40, and now we are able to see more information about the device and its capabilities. For example, the card in example supports up to 393,080 queue pairs and more than 65,000 completion queues. Also, each completion queues can have up to 400,000 completion queue elements. We can also retrieve information about the adapter's physical ports. In this case, the adapter card has 2 ports, and the first port runs Ethernet, and the second runs InfiniBand, and the ports are up and active. In this tutorial, we will learn how to allocate a protection domain. A protection domain is a way of gathering resources into groups. Resources of the same protection domain group are allowed to interact with each other, while resources of different protection domains are not allowed to do so. Let's allocate a protection domains by calling IBV ALLOC PD. This will return a pointer to the allocated protection domain. By opening the device, we can assign a context and a pointer to the protection domain that we are going to use in the next few steps. To proceed, click the question mark icon to learn more about IBV ALLOC PD. This tutorial will explain how to register a memory region. In order to perform RDMA operations, it is necessary to grant the network adapter permission to access local host memory. This is done through a resource called memory region, while creating a memory region is known as memory registration. A memory region has an address, a size, and a set of permissions that control access to the memory pointed by the region. In order to register a memory region, we need to call IBV regmr. The call argument includes the protection domain the region is assigned to, the start virtual address of the memory region pointed by the registration, the size of system memory covered by the region, the access permissions flags, local read, local write, remote read, remote write, and atomic operations. Local read access is required when the adapter has to gather data from local system memory when initiating a send or RDMA operation. Local write access is required when the adapter has to scatter data to local system memory when receiving a send operation. Remote read access is required when the adapter has to gather data from local system memory when processing an RDMA operation on behalf of a remote initiator. Remote write access is required when the adapter has to scatter data from local system memory when processing an RDMA operation on behalf of a remote initiator. Atomic operation access is required when the memory region is targeted by atomic operation. To proceed, click the question mark icon to learn more about IBV regmr. This tutorial will explain how to create a completion queue. A completion queue is the interface used by the adapter to notify the application about the status of completed work requests. Each entry in the completion queue, CQE, represents the completion status of one or more completed work requests. Completions for a send queue and a receive queue can be assigned to the same or different completion queues. We create a completion queue by calling IBV create CQ. Let's review the function parameters. Context is the RDMA device context that was returned from IBV open device. CQ size is the minimum capacity of the CQ. The actual capacity of the specified CQ is returned by the call. The next three arguments, CQ context, channel, comp vector, are only necessary when dealing with completion events. Completion events are not covered by this example. We will learn more about them in a later section. IBV create CQ will create a pointer to the newly allocated completion queue and will return the actual size of the completion queue. To proceed, click the question mark icon to learn more about IBV create CQ. So far, we created most of the needed resources to start sending and receiving packets. In this tutorial, we will learn how to create a queue pair. A queue pair consists of a send queue and a receive queue. An application will submit a work request to a send queue whenever it wishes to send data, or will submit a work request to a receive queue whenever it's expecting to receive data. We will create a queue pair by calling IBV create QP using the protection domain we created earlier and the structure IBV QP init attr. Let's take a closer look at this structure. QP type is the transport service type requested for this queue pair. In our example, we use unreliable datagram, UD. Cap describes the attributes of the queue pair send and receive elements. We will see its details later. Send CQ is the completion queue assigned to the send queue, as returned by IBV create CQ. RECV CQ is the completion queue assigned to the receive queue, as returned by IBV create CQ. In our example, we will be using the same completion queue for send and receive. Let's get back to the cap attributes. Max send WR is the maximum number of outstanding work requests that can be posted to the send queue. Outstanding means pending before completion. We need to make sure that this number is smaller than the number of entries in the CQ in order to prevent the CQ from getting overran. Max RECVWR is the maximum number of pending work requests that can be posted to the receive queue. Max send SGE is the maximum number of scatter/gather elements that can be posted in a send queue work requests. In our example, we use a value of 2, so we can build messages using up to 2 scatter/gather entries. Max RECV-SGE is the maximum number of scatter/gather elements that can be posted in a receive queue work request. The maximum number of scatter/gather entries supported by the device can be retrieved by invoking IBV device query. We are now ready to create the Q pair by calling IBV create QP. The return value is a pointer to the newly allocated Q pair. To proceed, click the question mark icon to learn more about IBV create QP. In this tutorial, we will learn how to bring Q pair to ready to send state. A Q pair must be transitioned through a sequence of states before it is capable of processing send and receive work requests. Each state transition has a set of mandatory and optional attributes. For simplicity reasons in our examples, we will be only covering mandatory attributes. For details optional attributes, please see Table 91 of the InfiniBand spec. The following simplified drawing helps us understand the basic states: reset, initialized, ready to receive, and ready to send. We move the Q pair through its states by calling IBV modify QP. Upon creation, a Q pair is in the reset state. In this state, the Q pair can't process any work request. Unreliable Q pair creation. In contrast to a reliable connected transport, where communication is only possible between two Q pairs, an unreliable datagram Q pair allows one-to-many communication without requiring a previous connection setup. For that reason, we have chosen for our first example to use an unreliable datagram transport. Reset to initializing state. This is the first transition needed to move the Q pair out of its initial reset state. Once the Q pair is transitioned into the init state, the user may begin posting receive buffers to the receive queue via the IBV post recv command. Note that posted receive work request in this state will not be used until the Q pair is in ready to receive state. The required attributes are P key index, primary physical port, Q key for unreliable datagram only. Q key is a part of the unreliable datagram protocol. All Q pairs that want to communicate over unreliable datagram service need to use the same Q key. Initializing to ready to receive state. The transition to ready to receive allows a Q pair to start processing incoming data into receive work requests. Here, we don't have required attributes. Ready to receive to ready to send state. The transition to ready to send allows a Q pair to start sending data by processing send work requests. In this state, the user may now post send requests with the IBV post send command. The required attributes are packet sequence number. This is sequence number of the first packet send from this Q pair. For unreliable datagram transport, this value is mostly ignored, so we can always choose PSN equals 0. To proceed, click the question mark icon to learn more about IBV modify QP. In this tutorial, we will learn how to create address vector. Before we can begin sending packets, we need to declare a destination. A destination is described through an object called an address vector. The address vector attributes are destination GID, as seen in the output of IB status command on the destination node. LS global is a flag indicating the presence of a destination GID. SGID index is the index of the source GID of our packets. For InfiniBand connection, we also need the destination lid. This can be retrieved by running IB status. SL and hop limit will not be covered in this course. They are set to default values. The address vector is registered by calling IBV create AH, which returns a handle to the created address vector. To proceed, click the question mark icon to learn more about IBV create AH. In the following tutorial, we will learn how to post work requests. Whenever we want an adapter to perform a send or receive operation, we need to post a request to one of the adapter's send or receive work queues. Send request defines all the properties of a send request. For example, how much data will be sent, memory buffer where data is located, to where data should be sent, the type of the send request, send, send only, RDMA write, RDMA read, etc. Receive request defines all the properties of a receive request. For example, maximum data size to be received, memory buffer where data should be written. In every work queue, work requests are handled in the order they were posted. There is no order guarantee between work request posted to different work queues. Requester, the side that submits send request. Responder, the side that process receive request. At this point, we are ready to post our first send work request. In this example, we will send the message, Hello UD. In this section, we will use our previously registered memory buffer. Following are the fields we will need to fill in our work request data structure. ID is a user-defined 64-bit identifier that will be returned in the completion element for this work request. SGList is a pointer to a list of buffers and their sizes where the data to be transmitted is located. NumSGE is the number of entries in the scatter-gather list. Opcode describes the type of operation we will be performing, in this case, IBV WR send. Send flags is used to set individual properties for the work request. IBV send signaled is used in this case to request the generation of a completion element once the data is transmitted. Next is a pointer to the next work request when a chain of requests is posted. In this case, we use null as we are only posting one element. It is time to declare a destination for our send. WRUDAH is address handle that describes where to send the data. We specify the target destination using our previously created address vector. WRUD remote QPN is the queue pair number in the destination address we want to target. We will show how to retrieve the destination queue pair number in a further section. WRUD remote queue key is the queue key value of the remote queue pair. In this case, we will be using a well-known queue key, therefore guaranteeing that all queue pairs in this example share the same queue key value. Finally, we can do a post-send request by calling IBV post-send. QP is the value returned from IBV create QP, and WR is a pointer to the first work request, and bad WR is a pointer to an array of bad work requests in case of failure. To proceed, click the question mark icon to learn more about IBV post-send. In the following tutorial, we will learn how to poll for completion. Transactions can be completed successfully or with error. Their result is reported through a completion queue entry. Polling a completion queue is used to retrieve the completion queue entry from the completion queue. The outcome of the transaction is reported in the status field of the completion entry. When the adapter completes a transaction successfully, a completion queue entry with status success is returned. When the adapter fails to complete a transaction, a completion queue entry with status error is returned. All outstanding transactions posted in the same queue pair after the failing transaction will be completed with an error syndrome. Only after a work request has a completion, the send-receive buffer may be reused or freed. By calling IBV poll CQ, we can retrieve work completions from a completion queue. Num entries is the maximum number of completions to read from the completion queue. In this example, only one. If one or more entries are found, this call returns the number of completion entries. This number will not exceed num entries. WC points to an array of completion queue entries to be filled in case completion were found. If no completions are found, the call will return 0. The call returns a negative value if the function fails. To proceed, click the question mark icon to learn more about IBV poll CQ. In the following tutorial, we will learn about IB dump. In order to see RDMA offload packets, it is not possible to use traditional sniffing utilities such as TCP dump because offloaded traffic bypasses the regular OS networking pipes the sniffing tools relay on. Instead, we can use a tool called IB dump for both InfiniBand and RDMA over converged Ethernet. The tool is executed by providing the name of the sniffing device and port number to be sniffed. The trace capture is written by default to a file named sniffer.pcap that can be opened by running tcp-dum-r sniffer.pcap. Let's start by running our sniffer tool in the following way. IB dump -d MLX40-I1. Now let's execute our second command, IBV basic send -d MLX40-I1-G and GID number. Finally, we can stop IB dump and read the parsed output where we can spot the text "Hello UD" in the data portion of the packet. In this tutorial, we will cover the required steps to build a receive application. We will rely on our previous send application, making the necessary changes to enable the receive data path. Let's look at the structure of a receive application. 1. Get device list. 2. Open the requested device. 3. Query device capabilities. 4. Allocate a protection domain to contain your resources. 5. Register a memory region. 6. Create a completion queue. 7. Create a queue pair. 8. Moving a queue pair to init state. 9. Post-receive work requests. 10. Moving queue pair to ready to receive state. 11. Poll for completion. And 12. Clean up. The receive side will receive data from a remote node. For that, it will need to scatter data to its local memory. Therefore, the first step we need to follow is to register local memory for our scatter with local write access. As you remember, by calling IBV regmr, we can register a memory region, and we now add the IBV access local write flag. An application should submit a work request to a receive queue before an initiator starts sending data. Receive CQ is the completion queue assigned to the receive queue as returned by IBV create CQ. In our example, we are using the same completion queue for send and receive. Let's go over the needed changes in our queue pair creation flow to enable its receive side. As this will be a receive-only application, we will change the value of send work request to 0. We will then change the number of receive work requests to the desired maximum number of entries. At this point, we are ready to move the queue pair to init state. Once in this state, and before moving further, We need to guarantee that we have allocated receives buffers for the incoming data, as well as posting receive work requests to the adapter. Receive work requests have the following format: ADDR. This is the address where incoming data will be scattered. Length is the maximum message size that we are ready to receive. In unreliable datagram messages larger than this size are silently dropped. L key is the protection key of the memory space we registered for the given address. We call IBV post receive to pass our work request to the queue pair. After posting all the needed receive buffers in init state, we are now ready to let the queue pair handle incoming data by moving it to the ready to receive state. As this is a receive-only queue pair, it is no longer necessary to move the queue pair to the ready to send state. We can stop the transition process at ready to receive. We use again IBV poll CQ to find out if new data arrived to our queue pair. IBV poll CQ can be used in the same way as we did in our sender side. When a receive work request is consumed, a completion entry will always be generated. The completion entry for receives includes source MAC or lid of sender, source queue pair, destination queue pair, destination MAC or lid index, size of the data scattered by the adapter. In unreliable datagram queue pairs, there is always a global routing header, GRH, written at the beginning of receive buffer, so the receive work request should always have extra 40 bytes for that purpose. Here we can see an example. Let's now start our receive side application. Run the command IBV basic receive-d Mellanox0-I1. We don't have to specify who is the remote side because we can receive data from any remote node as our transport is unconnected. In this example, we can see the receive side linked to queue pair number 4C. We need to look at the output of our command and gather the following parameters needed for our send side application. We need to provide the receive queue pair number, the destination GID. For Rocky version 1, the destination MAC. For Rocky version 1.5 and version 2, the destination IP. For InfiniBand, destination LID. With all this data, we can run IBV basic send. Now we can see at the receive side the output message hello UD. We can also use IB dump to look at the incoming traffic.